Hi all. So today we are going to be fitting discrete distributions of data using SciPy. Now the first thing we're going to do is we're going to create the folder structure for our project. And we're going to want to create that on our user folder. So we're going to go ahead and create new folder. And let's call this folder projects. And in projects, I'm going to create another folder. And we're going to call this, we're going to call this folder Scientific Python. And in Scientific Python, we're going to create our final layer called Fitting Distributions. Now from here, what we're going to want to do is open up Pycharm. This is my preferred IDE for working with Python. It is a fully integrated IDE that has IntelliSense and will complete a lot of the code for you. And it also has some nifty features for being able to set up our own interpreter and figuring out what different packages are installed. So we're going to go ahead and open a new project. And we're going to go down to the users folder. And we're going to locate the project folder that we created, Fitting Distributions. Now that our project is open, we're going to want to create a new Anaconda environment. Now, Anaconda is a package manager for Python. It comes standard on all Sizer servers. And what this allows us to do is create a virtual environment in which we'll install all of our Python packages. So we're going to do Anaconda create --name fitting distributions, and the version of Python that we're going to use is 3.6. And as you can see, I'm doing this all from the terminal here. All right, so our VNV, our virtual environment, is created. We're going to now activate it, so activate fitting distributions. And now we're going to install some of our packages. So conda install numpy, not jumpy. Whoops. Conda install numpy. Conda install SciPy. These are the two main packages that we'll be using for this project. In addition to these, we will be working with scikit-learn for a complete set of data sets. So conda install scikit-learn. And for plotting our data, we're going to be using matplotlib. Looks like we're stuck. installed. So now we're going to go ahead and create the main file, distribution.py. Now distribution.py is going to be home to our distribution class. This is going to be useful for modeling distributions based on discrete data. So first we're going to import SciPy. We're also going to import SciPy.stats. Before we do that, actually, we're going to configure the Python interpreter for this project. We're going to add a new interpreter from our Conda environment. This is going to be Conda 3.6. I'm going to use fitting distributions. This is an existing environment. I'm going to say OK. And we're going to accept these changes. And click Apply. There we go. And now we're going to complete our imports. Matplotlib as import pyplot as plt from sklearn.preprocessing import min-max scalar. And I'm going to explain what these things are in a second. So the first thing we're going to do is we're going to name all of the distributions that we're going to want to test for our data sets. Now these are going to be a series in a tuple. The reason we're choosing a tuple is because we're creating a global scope here, and we want to make sure that all of our distribution names are immutable. We do not want these changing after we name them. So these are our distribution names: exponential, gamma, logarithmic normal, normal, Pearson 3, etc. Now we're going to write the actual class itself. Class distribution. Now the first thing we want to do for distribution is define the init method. And the init method is going to take in a list of distribution names. Now here we're setting the default argument for dist names list to be the dist names we named up here. Now what this is going to do is mean that every time we initialize a new distribution class, it's going to test against the distributions in dist names. From here, we're going to do self.distNames equals dist names list. Self.distResults equals empty list. Self.params equals empty dictionary. And now here, self.distribution name is empty string. Self.correlation value is equal to none. Self.param is equal to none. Self.isFitted. This tells us whether or not we have fit the data to any given distribution. And this should be false. We have not fit anything yet. And self.scalar is equal to none. We're going to initialize all these things in the following parts. Now what we're going to do is we're going to write the main method for this program. This is going to be our fit method. Now fit is going to take in a bunch of y data. This is just an array of randomly sampled data. And we're going to try and fit a normal distribution to this, or one of the distributions in dist names to this. Also forgot to import a standard scalar here. So first thing, SC is equal to standard scalar. Now we're going to reshape the y's to be a column vector. This is a NumPy method, and this is a NumPy array. Make sure that you note the types there. And now we're going to do fit transform yy. What this does is it transforms the column vector of data we received before to have unit variance and mean 0. This is useful because when we're receiving data from lots of random variables, we need to standardize it in such a way that the data can be processed by the library. Now we're going to go ahead and flatten the list. Oh, gotta reassign it here. Self.dist results equals blank list. This is just reinitializing dist results to be empty list in case we already fit it to a different distribution. Self.params equals empty dictionary, same thing there. Now for each distribution name in self.distNames, we're going to perform a KS test. So dist equals getAttr SciPy.stats distName. This is important. GetAttr returns the attribute named by this string distName. Now if we're passing in the default names of the distributions, those are all listed up here. So we're essentially picking one of the distributions and performing this test. This is a nice way to make it extensible, so that if you wanted to add more distributions to test, you simply have to name them up here or pass them into this distNames list argument for when we instantiate the class. From here, I'm going to say param equals dist.fit yy, self.params dist name, we're adding the dictionary argument, is equal to param, and self.param now what we want to do is perform the KS test, so SciPy.stats.ks test. Our random variables are yy using distName, and the args are equal to param. Now self.dist results, we're going to append the results of this test, distName, and p. P is our correlation coefficient. We have now successfully fit the data. We're going to delete that array of y's that we had, and we're going to select the distribution with the maximum p-value. So this is equal to max self.dist results key. The key argument allows us to pass in our own comparator function, which will take in an item and return the second argument of the item, which in this case in Python is index starting at 0, so we want index 1. Now what we do is we set distribution name equal to selDist. This is the best distribution, the best correlation value that we have found. And we set self.p-value is equal to p. This is the best correlation value we found. Now we set self.param equal to self.params selDist. And finally, we set self.isFitted equal to true. This tells us that the data has been fitted. Now we return self.distributionName and self.p-value. This just returns what the correlation is between our fitted distribution and the random variables we have sampled. Alrighty. The next thing we're going to want to do is write a function that gets random variables from our probability distribution. So what we're going to do is we're going to define a function random, and we're going to give it a default argument of 1. This is the number of random variables we're going to use. Now, we're going to say if self.isFitted, so the distribution has been fit, and say distName equals self.distributionName, param equals self.params. Now, Now I'm going to say dist equals getAttr SciPy.stats and dist name. This is just the same thing we did before in doing the KS test. And we're going to return dist.rvs star param up to -2. This is just the arguments of the parameter, if there are any. Lock equals param -2. This is the location argument. And scale equals param -1. This is the scale argument. And now the size is going to be n. This is by default 1, so we're just using one random variable. Now if the distribution isn't fitted, we're going to raise an error. We're going to raise a value error. And we're going to say must first run the fit method. So this just means the data needs to be fitted before you're able to actually generate any random variables. Now what we're going to do is write a really simple plot method that allows us to plot the random variables generated by from this distribution against some other one. So we're going to define plot self and y. X equals self.random and equals len y. So we're plotting the same number of variables as the length of the y list. plt.histogram x alpha equals 0.5. This is just some matplotlib styling. This is going to be called fitted. And now we're also going to plot plt.hist_y, alpha equals 0.5, label equals actual. Now plt.legend, we're just going to create the legend, and we're going to put this in the upper right corner of our distribution, or of our plot. Now, we're also going to add in some other functions just to mimic the probability point function and the cumulative distribution function. These are essentially just wrappers from SciPy. What PPF gives you is the inverse of the CDF. What the CDF gives you is the cumulative distribution function. So if you learned about that in your stats class, or have experience with any sort of basic probability theory, you'll know what this is. All right, so in the next video, I am going to show you a little demonstration with this class, and we're going to plot some stuff. So yeah, we'll see you then.